Hello, everyone. You made it. It snowed, and you still made it. Thank you for that. Welcome to CS4U Day in the Cheriton School of Computer Science at the University of Waterloo. And I'm glad to see so many young, bright, enthusiastic faces and your teachers here this morning. So CS4U stands for Computer Science for You. And by you, I mean not me, but you. If you were saying you, you'd be talking about me, but I mean it for you. The you you'd mean if you said me. So, so one thing you should know today, first of all, it's great to have you here because this is the live audience. You're actually here, so congratulations for that. We also have a dead audience. No, we have a webcasting audience that's out in the internet watching a live webcast. It's actually not entirely live. It's slightly delayed. You're actually here, so. Can you hear this? We also have a dead audience. No, we have a webcasting audience. Can you hear that? I was going to interview myself. It's about a 20-second delay. That might be awkward. Well, you can see that. Let's see if we can get a bit of a close-up here. This is getting trippy. I was going to ask what things were like 20 seconds ago. What was it like? Look at that, camera on camera on camera. So this is being broadcast live. He was bugging me. So it's being broadcast live. If you're out there watching the webcast, I was just wireless, but we really advise you to be plugged into an Ethernet cable because things can get sketchy if your internet connections come and go. So, and also if you're out in webcast land, there's a way you can email in questions. So look on the CS4U webpage and then find out how to take part in what's going on here. What else was I going to say? Right, okay, this is also going to be on YouTube. So sometime in the future, it'll be on YouTube. So hello, future. Hello, future. What's it like? We'll talk about that in a little bit. I do have a few quick notes before we get started. We have washrooms. Take that, U of T. So the washrooms are, you exit the auditorium, turn right, and there they are. If you're watching the webcast, that doesn't apply to you. You can just poop in your pants, I won't smell it. We have garbage cans also, thank you. Yeah, thanks. All right, so use those. And also, just for fire regulations, we should keep, I see that there's no problem here, but keeping the aisles open. We have exits here at the front. We do expect the building to burn down today, so make sure you know where the exits are. This is Math 3, by the way. We have 3 math buildings here at Waterloo. I think they should have called it Math 18. That would have sounded more impressive, but called it Math 3. Okay, so to get things started, I'm going to ask David Taylor, the director of the school, the Cheriton School of Computer Science, to come up and say a few words.
Good morning. On behalf of the faculty, staff, and students of the Cheriton School of Computer Science, I'd like to welcome you to CS4U Day at the University of Waterloo. I assume most of you are students interested in computer science, but we also have teachers, parents, and other friends with us today, and I'd like to welcome all of you and thank you for joining us. Jeff has already mentioned that we're in Math 3 and that means that we have 3 math buildings in spite of his apparent desire to call it Math 18. This building, in fact, houses primarily statistics and actuarial science and the math business program. So computer science sort of doesn't belong here, but we do have this nice new presentation room which is suitable for this, and so the statistics department is letting us use the building. The other 2 buildings that the math faculty is housed in are connected to this one by overhead bridges, so if you just go outside, you can see the pedestrian bridges connecting it to the other 2 buildings. The Davis Center, which houses computer science, and the original math and computer building, which houses the remaining 3 departments. They're very easy to tell apart. If it's metal and glass and brightly colored, it's the Davis Center. If it looks like a concrete fortress, it's the original math building. When I was the age that most of you are here, computers were large boxes kept in air-conditioned rooms, and they were just beginning to have an effect in everyday life. But today, it's hard to imagine a world without information technology. Those of you thinking about becoming a student in computer science have grown up in a society filled with personal computers, Wi-Fi, smartphones, and digital cameras. Information technology has become so prevalent that words we use to describe it, like internet and database, have been added to the dictionary. Finding answers to our questions no longer involves a trip to the library. You can discover where Albertosaurus was found, who invented Trivial Pursuit, how to make chocolate chip cookies, or how to spell hyphenate by Googling a few words or by using the online Oxford Dictionary. You can do all of this very quickly and efficiently, whether you're at home, in your classroom, or elsewhere. And when we do go out into the community, computer technology makes it possible for us to complete tasks independently. You can check out of the grocery store by scanning barcodes, access banking information electronically using your PIN, or you can use GPS and online maps to find out where you are, where a place of interest is, and how to get from one to the other. Computer science is about solving the problems that underlie all of this technology. How to find an answer faster or search a large database of information to find a specific piece of data. How to send information from your personal computer through networks and servers to a machine at the far side of the world, and to do this securely and privately. How to build a software system containing millions of lines of code that functions reliably and can be extended and maintained for years. The Cheriton School of Computer Science is the largest in Canada, and our faculty work in a very broad range of areas, from algorithms and complexity to bioinformatics to artificial intelligence to human-computer interaction to, and so on. Each of our faculty members is passionate about his or her own area. A few of them will be speaking today about topics that excite them, and you'll have a chance to participate in hands-on activities as well. In just a few moments, Professor Lubiu will explore algorithms using a Rubik's Cube. Later on, Professor Lank will explore how smartphones interact. These activities should give you a glimpse of what is at the heart of computer science, a desire to design a technical solution to a problem, and by doing so, improve some aspect of our society. I hope your visit today will excite you about the possibility of studying computer science and possibly making it your career. If you are interested in further studying computer science, the school holds other events each year for students who are interested in finding out more about our faculty and our facilities. So thank you for attending CS4U, and enjoy your day.
Thanks, David. I just want to, first thing I should mention is the speaker we originally had for after lunch, Peter Van Beek, because of unforeseen circumstances, won't be speaking today. We have something else planned which I think you will like. Unfortunately, it's something that we can't stream live, so people out there in watching the webcast, any teachers, sort of banking on that time, maybe you can watch another of our YouTube videos from last year or something. I apologize for that. I want to reiterate something, Dave. Oh, by the way, I'm Jeff Orchard. I didn't introduce myself. I'm a professor. Yeah, I think so. I just want, something I like to do sometimes is imagine going back in time. So imagine you go back about 15 years to when you were born, and imagine describing what things are like today to your parents. Okay, that's around 1996, right? Are you guys about 15, 14? 1997. In that area, okay. If you were to go back to that time, you would notice that your dad's new computer has 32 megabytes of memory. And you'd say, geez, Dad, you can't even buy a smartphone with less than 32 gigabytes of memory. Gigabytes, that's 1,000 times as much as a desktop from 1996, 1997. And so, I mean, cell phones were rare back then. So your dad might say, why do you even need that much memory on a cell phone? Well, if you're like, well, it's the operating system and, you know, the web browsers and Googling. And you give you a blank stare and say, web? What's the web? Believe it or not, the web was invented in 1993. The web didn't exist before that. I mean, what could be more fundamental to your lives right now than the web? So obviously Google didn't exist. So imagine trying to explain to your mom and dad back in 1996, okay, you're out biking with your friends and you want to find out who the last 50 winners of the Tour de France are. How do you do that? Well, you pull out your smartphone and you Google it. That didn't exist in 96. You'd have to run your butt to the library and start looking up books and find out, you know, instead Google gives you like what, the 2 million most relevant web pages. Okay, that sort of thing, that reality is a result of computer science. Okay, computer science made that happen. Another revolution, how do you get a song that you want? Do you walk to the music store and buy a CD? No, you download it from iTunes or maybe somewhere else. I don't want to hear it. Why? How did that happen? Because someone with a mind for computer science wrote a program that completely overhauled the music industry. And we're seeing that phenomenon over and over again in different industries, in different parts of your life. Social networking, that didn't exist 12 years ago. Heard of it? So now let's do another thought experiment. Instead of thinking back 15 years, think forward 15 years. That future is going to be even wilder than you can imagine. There are going to be revolutions that will take place that we cannot understand. Okay? And I feel confident in suggesting to you that computer science will play a fundamental role in the way that future turns out. Okay, there will be changes that happen in the next 15 years that haven't been invented yet. Haven't been invented yet. Okay, so I think computer science, I mean, we're in the information age. What is computer science? It is the analysis, the theory, the practice of information processing. And in the information age, you hold the cards. So now you ask yourself, what part of that future are you going to take? So I want to introduce our first speaker. Her name is Anna Libu. And I'm not done yet. She does computational geometry. So a lot of her interests sort of center around geometry. So knitting, for example, she knits, that's a geometrical thing to do. Origami, she does. She also likes maps. She also likes science fiction and gardening. She also plays the violin in an orchestra here on campus. But today she's going to talk to us about the link between computer science and Rubik's Cube, which I think you've all got in front of you. Anna Libu.
Okay, thank you very much, Jeff. The mic is fine? Good. So, I'm going to tell you about the Rubik's Cube. How many people have a Rubik's Cube at home? Okay, you just got another one. This is a puzzle that was invented by a Hungarian architect in 1974. So this is one of the original Hungarian packaged Rubik's Cubes, and I actually have one of those from the 70s, which sort of dates me, doesn't it? A little bit after that, they were sold in North America, and they were sold in a package that had a sign saying, over 3 billion combinations. Now, in fact, there are more than 43 quintillion combinations in every Rubik's Cube. And that means 43 times 10 to the 18th. That's a huge number, 18 zeros after it, instead of the billion, which only has 9 zeros after it. So as Douglas Hofstadter said in an article about innumeracy, this is sort of like McDonald's saying that they've sold 120 hamburgers. It's off by that magnitude of scale. So why do you think they put a billion on the package? It's just because they didn't think people would understand a quintillion. So the Rubik's Cube in those years since the 70s has become sort of just a part of our culture. There's art made with Rubik's Cubes. You can buy all sorts of things with Rubik's Cubes on them. And I'd like to start with a few basics of terminology. So if you look at the Rubik's Cube you've got, there's 3 different kinds of little cubies on there. There's the ones where you see 3 colored stickers showing, the ones where you see 2, and the ones where you see only 1, right? So let's first just count how many of these there are. So how about these corner cubies, the ones with 3 stickers showing? How many of those are there? How about calling it out? 8. Okay. So next we're going to talk about the edge cubies. These are the ones with 2 stickers showing. And you can count them or think in your head or something. How many of those are there? 12. Great. I see there's a whole bunch of people still just coming in who need Rubik's Cubes to catch up with where we are. Maybe I'll give you guys just a minute or two to sit down. So maybe I'll try to start again here. Welcome to those of you who are just coming in late. I'm hoping that you will soon have in your hands a Rubik's Cube and can join the rest of us. We're thinking now about how many of the 3rd kind of cubies there are in a Rubik's Cube, namely these ones that have only 1 colored face showing. These are called the center cubies. So how many center cubies are there on your Rubik's Cube? 6. Great. So this one I don't want you to call out because I think there's more than one legitimate answer. But how many cubies are there altogether in the Rubik's Cube? Someone put up your hand if you have an answer. I see one answer here. How many?
27.
27. That's a great answer, and I bet you got it. Sorry?
Is there one in the middle?
Yeah, she's counting the one in the middle. So she's multiplied 3 times 3 times 3, 27. And there's that one in the middle that you don't see at all. So the alternative legitimate answer is to add up these 3 numbers that appear here and say there's only 26, because that one in the middle doesn't count. So 2 possible answers. Okay. Now, the point of my talk will not be how to solve a Rubik's Cube. I am guessing that there are some people in this audience who are very good at doing that. I myself confess that I don't really know how. I once worked it out, and it took me 3 months, but I don't still have in my head the method that I used. That was in those days that Jeff was talking about before the web, where you couldn't just look up how to solve a Rubik's Cube. But if we were to think from scratch how to solve this, the main idea is to start small. That's how you start solving any problem. So we have the corner cubies, the edge cubies, and the center cubies, and we need to get them all in place. And there's one good thing right away, that among these three kinds of cubies, the center cubies are already solved. As you turn this thing, center cubies aren't going anywhere. They're always staying fixed. So they're already solved. We only need to solve the 8 corner cubies and the 12 edge cubies. So I would like you all to at least make the first steps towards solving a Rubik's Cube. I know this will be boring for the few of you who have already been making super flip over there. But here's your first goal, which is to get the white cross on top. So find that white center cubie, put it on top. That's easy. You just turn your cube to put it on top. Now find those edge cubies, those 4 edge cubies that have a white face, and try to do some turns. Oh, hey, I know what. I forgot to ask, how many people had kept your cube in a pristine state up until now? Oh, you're so good. If we were going for a walk in the woods and there was a chance of getting lost, you guys are the people I want to be with, because you wouldn't make a move unless you know how to get back. But listen, now is the time to jumble this up. Otherwise, this activity will be no fun. So jumble it up. Mix it up. Mix it up all together. It doesn't take very many moves to mix it up. See what the progress is like. How many people have managed to get at least one of those white side guys in the right place? Okay. Now, one thing I would like you to notice is that by getting them in the right place, I want it not only to be white on the top here, but I also want it to match on the side, okay? So like that white and blue one, the blue matches the blue in the center of that face. So see if you can try to do that with at least 1 or 2 of those white side pieces. How many of you have all of them in place already? Okay. I think there's some people who know how to use cubes already. So let's, I know some of you probably don't have all of them there, but I'm hoping everybody has at least one white side cube in the right place and has had the satisfaction of, seeing a little bit how the turns affect the cube. The second goal is to get the corner cubies of the white face in the right places. And for that, I would like to show you something else. Rather than inviting you to try to think of it yourself, I'd like to show you a little method that's kind of fun to do and that will work for this. So it's easy enough to get one of the white corner cubies in the bottom below where it should be. And then here's a simple method to get it up into the top. Now, to show you what it is, I need to talk a little bit about the notation that's usually used for moves of the Rubik's Cube. So people label these faces. There's the right, the left, the up, the down, the front, and the back. And they keep the cube always in the same position in front of them. And then when you say R, you mean to turn the right face clockwise. And R prime means counterclockwise. So with that notation, the sequence of moves I want to teach you about is you do the right face counterclockwise, then the down face counterclockwise, then the right face clockwise, and the down face clockwise. So right prime, right, down. And I have a little movie to show how that works. So let's see if the audio is working here.
Right inverted, right, down. That same one that I showed you in the algorithm demonstration. Now, you're going to need to do this multiple times until this is in the correct place with the correct orientation. So repeat it. Right inverted, right, down. Right inverted, right, down. Right inverted, right, down. Right inverted, right, down. And there it is.
Okay. So try it out on your own cube. You've probably memorized that by now, having heard it so many times. It doesn't matter, by the way. Okay, hush for a minute. It doesn't matter if you have those little edge cubies in the right place or not. You can still attempt this move. Okay? Now, I'm not going to tell you more about solving the Rubik's Cube. That first layer is relatively easy to do, and after that, things get a little bit harder. And the reason is that now you have some of the cubies in the right place, and you want to keep them there as you solve the other things. So, but if you want to learn how to solve a Rubik's Cube, there are great resources on the web. I was getting some of those pictures from this website, and that little video was coming from YouTube. So if you when these slides are available on our webpage, you can go and look for this, or you can just search how to solve a Rubik's Cube Part 1, and you'll find it. There's also virtual cubes available on the web in case you get tired of the physical manipulations. For me, that's part of the fun of it, is the physical object. So, but in any case, learning to solve a Rubik's Cube, you know what? Anybody can learn to solve a Rubik's Cube.
Okay, Amy, you can go. Okay, Amy, you can go.
Touch up a little bit. That's pretty incredible, right? Remember that time he got? 5.66 seconds? Look, here's something that beats it. I'm going to turn the sound off on that one. It's just a lousy music. Now listen, as you're watching this, is this turning faster or slower than Felix was? The actual turns. Which do you think was faster, Felix or this machine? Felix was faster, but he used more turns. So the best speed cubers, like human speed cubers, can manage a staggering 9 moves per second, but this Lego device averages only about 5 moves per second. It's just smarter than the people. It manages fewer moves. So there are also competitions where people try as a group to see how many people can solve a cube in a certain amount of time. And again, recently, 2010, 134 schoolboys managed to solve Rubik's Cubes in 12 minutes each. So I'd like to tell you a little bit about some of the different algorithms for Rubik's Cubes that are out there. The oldest ones come from just shortly after the cube was invented, so like the 80s. And they worked layer by layer, which was the method I was telling you about, where we solved first the white layer. Jessica Friedrich, for example, who competed in the 82 World Championship when she was 17 years old, she had an incredibly complicated method, but it managed 55 moves on average to solve the Rubik's Cube, which is really good. Philip Marshall had a method that went in sort of the opposite direction. Instead of having to memorize a lot, you had to memorize only very little, but it averaged 65 moves to solve the Rubik's Cube. So there's this sort of trade-off between the number of moves and the difficulty of memorizing what you need to do. So let's look at this question. The bottleneck for, how could Felix get faster? It would be to learn a method that involves fewer moves. But what's the bottom line as far as what's the minimum number of moves you can get to there? So certainly this depends on how mixed up the cube is, right? If it's only one turn away from fixed, then one move will solve it. So what we're going to look at is the most jumbled up cube and ask how many moves to solve that. And certainly it also depends on the algorithm, but we're going to think of what is the absolute best algorithm that uses the minimum number of moves possible. So this number, how many moves to solve the most mixed up cube with the best algorithm, this is called God's number. Now, whether you're religious or not, I hate this name. I happen not to be religious, but I think it's a lousy name. But it's what people use, so that's what I'm going to call it. The idea is that if God were solving the Rubik's Cube, this is the number of moves that God would make. So it was known already in 1995 that this configuration of the Rubik's Cube, which is called super flip, because it's got all the edge cubies flipped the wrong way. And I saw a couple of people here make it when they first got their Rubik's Cube. It was known in 95 that this takes 20 moves. You cannot solve this Rubik's configuration in fewer than 20 moves. Now, I'm going to show you in a video how to solve it in 20 moves, which doesn't show that you can't do fewer, right? You need a computer search to verify that. But let's watch. Count with me here that this is 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, and we went from the fixed Rubik's Cube to the super flip configuration, but obviously if you run it backwards, you sort it out. Okay, so the question that remained back in 95 is, are there some configurations, like different from the super flip, that even take more than 20 moves? And that was only solved recently. So that blue arrow is showing the situation in 95, when it was known that super flip takes 20 moves, and the best upper bound people could show was 28. every Rubik's configuration could be solved in 28 moves, and it took 15 years to get that upper bound down to match the 20 and prove that for sure that superflip is the worst configuration. There's no other mixed up Rubik's configuration that takes more than 20 moves. So let me tell you the tiniest bit about how this group of people showed this in 2010. First of all, they cut down the number of configurations they had to examine from that total number of configurations, the 43 quintillion, down to just 56 billion. Okay? Then they wrote a computer program to check those, and each configuration took 20 seconds. That's more than Felix took, right? So why do they take so long? It's because they're trying to find the minimum number of moves, not just solve it, right? So, and then to try all those billions of possibilities at 20 seconds apiece took them 35 CPU years. That is, if you had one computer running it, it would take 35 years. What they did was use many computers, Google computers, simultaneously to do it. Now, they also examined the number of configurations that are different number of moves away from solved, and they have this thing saying distance 20 positions are both rare and plentiful. They are rarer than 1 in a billion, and yet there are probably more than 100 million such positions. And you can see that sort of the peak comes at about 18 moves away from solved, I think. Okay, do you think a person can achieve less than or equal to 20 moves? What do you think? How many bet that a person could? How many think that a person couldn't? I sort of favor couldn't, but I don't know. The human memory is amazing, so I'm not sure how much I would bet on this. But, you know, maybe probably not. Could a computer achieve less than or equal to 20 moves? I'd imagine so, but I don't think it's going to win any speed competitions doing it. Remember, it took 20 seconds of CPU time to solve each configuration and find the minimum number of moves for it. So that's more than it took Felix to solve the cube, right? So it's not in the speed realm. Now, one thing you might be thinking here is, well, it should be easy for a computer because there's just a finite number of configurations. Why don't I just store the right answer for each of those? And with this 43 quintillion different configurations, the amount of storage you would need to even write down the first move in all those solutions is already looking at exabytes of storage. So here's my little chart. You've heard of gigabytes, terabytes, maybe you've even heard of petabytes, but we're going up even to exabytes amount of storage, and that's out of reach. Okay, now I had promised to tell you something about math and computer science and the Rubik's Cube, and so far there hasn't been very much of that. So let me tell you a bit about how mathematicians think. Mathematicians like to generalize, and mathematicians like to make things abstract. So if you are the kind of person who sees a camel and says, well, what if it had more humps? You're thinking like a mathematician. On the other hand, this poor soul here who got 0 on their quiz did not realize this unspoken rule of mathematicians that x doesn't really mean x itself. It's an abstract variable that stands for a number. So mathematicians take for granted this kind of abstraction. And actually, that's one thing I love about the Rubik's Cube is it's not abstract. It's concrete. Here it is. It's geometric. It's tangible. You get to play with it. This is the kind of math I love the best. Anyway, for those of you thinking of camels with more humps, what should you do with the Rubik's Cube? You should generalize. So here are some bigger Rubik's Cubes. You'll notice the dates on this, 2007, 2009, for making these bigger Rubik's Cube. What took so long? Well, it's just getting the mechanics inside that's difficult. You can find virtual cubes that go up to 100 by 100 by 100. It's just a physical device is hard to make. Do people want to hush up a little bit? Just be polite so that your neighbors can listen if they want to, okay? I know you're all multitasking and playing with your cubes, which is great and fine, but keep the conversation down just so that people can listen. So in 2011, the biggest cube that's ever been made is this 17 by 17 one. It has about 1,600 little pieces, and you can watch a video on YouTube of the guy who invented it, taking it apart. It takes him a long time, even just to mechanically take it into its little pieces. You can buy these on a site called Shapeways that does 3D printing. That's how these are made. 3D printing, by the way, is going to revolutionize your lives. When Jeff Orchard was talking, imagine 15 years in the future, what will change? It's 3D printing, that you will not imagine how you existed without it. So, yeah, here I have a picture for engineers of the scheme that's used inside some of these giant Rubik's Cubes. And I have a little joke for the engineers. To the optimist, the glass is half full. To the pessimist, the glass is half empty. And to the engineer, the glass is twice as big as it needs to be. Oh, and I actually had a joke also about mathematicians that I forgot to tell you with that slide about math and the Rubik's Cube. So let me tell you that one. So there's a statistician, a biologist, and a mathematician. And they're assigned to watch a mysterious house where there's some mysterious goings on. So the house is empty, and they are set outside the house to watch the house and these mysterious happenings. And after a while, 2 people enter the house. And after a while longer, 3 people leave the house. And the statistician says, oh, it's just a statistical error. And the biologist says, aha, they reproduced. And there's a guy on the street who says that house wasn't empty in the first place. But the mathematician, who can do a little bit of arithmetic, says, well, if one more person enters the house, then it will be empty again. You doing the arithmetic there? Okay, so there are other generalizations of Rubik's Cubes, but I'm going to be sticking to the cubes, okay? And I'd like to tell you something about that. Now, do people do speed cubing on these? Yes, they do, but look at this record time here, 1 hour and 6 minutes. I will not show you the video of this solve, though in fact the video is only 10 minutes long, so they already cut from the full solution time. And let's look at how many configurations there are of some of these bigger cubes. So we go from 43 quintillion to, I don't even know how to pronounce these words. So 7 times 10 to the 45th for the 4 by 4 by 4 cube. And 10 to the 72 for the 5 by 5 by 5. So I have here a 5 by 5 by 5 cube. You can buy them in town at J&J Cards, for example, probably other places. It's incredible to think that this sort of captures a number of possibilities that's approaching the number of atoms in the universe. Isn't that incredible? Now, if we get even bigger than 5, the more useful way to think of this is in terms of the rate of growth of the number of configurations as n goes up. So I have 4 by 5 by 4. What if n is bigger? 5 by 5 by 5. What if n is equal to 17, like this over the top? So I'm looking at 17 by 17 by 17 Rubik's Cube. Now, we know that already for n equals 3, we have a huge number. And it doesn't stay the same as n goes up, right? We saw that in the previous slide. Does it go up like this curve? This would be the number of cubies counting the ones inside, this curve of n cubed, n times n times n. No, the number of configurations of the Rubik's Cube grows even faster than 2 to the power n squared. So it's an incredibly fast-growing function. It starts high, and then it grows incredibly quickly. So let's talk a little bit about how many moves it takes to solve a Rubik's Cube. For that, we were seeing that for the 3 by 3 cube, it's just 20 moves. Even though the number of configurations is huge, the number of moves is small. So let's look at the rate of growth of the number of moves you need to solve a Rubik's Cube as n gets bigger. We go to the 5 or the 17. So this is something that I worked on with some colleagues at MIT, the Massachusetts Institute of Technology, and we had a paper about this that appeared in a conference this summer. So there's a little picture of the first page of the paper, and the thing we showed was that God's number, this minimum number of moves to solve a Rubik's Cube, the way it grows as the cube gets bigger is a very nicely well-behaved function, n squared over log n. So let me show you that as a graph. I know that many of you don't know what log n means, and it doesn't matter, okay? So this 2 to the n squared was the graph of the number of configurations. It starts already at 43 times 10 to the 18th, and it grows incredibly fast. But the number of moves you need is this very nice small function, n squared over log n. It grows less quickly than the n squared function. So that was our result. Let me tell you the tiniest bit about my co-authors here. So Sarah and Andrew are graduate students at MIT. I'm not in this photo because it was taken after I left. I was there for a year visiting, and they took the photo afterwards. Eric Demain is a researcher at MIT, and he did his graduate work here at the University of Waterloo. He was 14 when he came to do a master's thesis, and he was 19 when he finished his PhD, and he went to MIT to be a professor. That was the record for the youngest professor at MIT. And he worked with me during his PhD time. And because he was only 14 going away to university, he came with his dad. That's a little strange, isn't it? But when you're 14, you're not ready to leave your parents. So this is his father, Martin Demain, who has stuck with him and is still doing research with him. And here's a picture of Eric's web page. He does a lot of really interesting things. His motto in life is to have fun doing research, and he has a lot of fun. He works on Rubik's cubes. He works on math of origami. That's what he did his thesis here on. He does glass blowing. He does improv comedy, and he leads a really fun life. Now, so far, the math that I've shown you has sort of been like facts about the Rubik's Cube. And I know a lot of what you're taught in math is also probably like facts. But the beauty of mathematics and the fun of it is not the facts. It's the pleasure we get in finding patterns in things and following logical arguments. So I would like to spend the last part of this talk trying to give you a little more flavor, not of the facts about math and the Rubik's Cube, but about why some of these happen. So I just have some pictures to say that mathematics is an ancient activity. I mean, yeah, maybe it was useful for counting sheep and, dividing up your farmland and building pyramids, but people also did it just because it's a human ability like music, and we take pleasure in exercising that ability. So I'm going to try to tell you a little bit about permutation groups, because that's what the Rubik's Cube is at heart. It's an embodiment of permutation groups, which is a very beautiful mathematical idea. So let's start by saying, let's look at the people in this room and ask, how many different ways are there to permute you? How many different arrangements of people might there be in this room? So oh no, that's not what this room looks like. You guys are much more awake. Maybe not quite as pink as this picture, though. So here, we're going to imagine that the room is empty and that there are, let's say, 352 seats and 352 people. And I want to count how many different ways are there to put the people into the seats. Now, if you think of the room being empty and the first person comes in, they have 352 choices of where to sit, right? The next person has only 351 because one seat's already taken. And we go on like this. The second last person has 2 empty seats to choose from, and the very last person has no choice. There's only 1 empty seat. So we have to multiply all of these choices together to say how many different arrangements are there of people in the room. Now, mathematicians have a shorthand way of writing this, 352 factorial, and we write that with an exclamation point. How many people have ever seen factorials in high school? Okay. My own kids claimed that they knew about factorials, but they'd never learned them in high school, which is, I don't know, kind of strange. Anyway, how big do you think 352 factorial is? Does anyone have a calculator? Some of you should be geeky enough to have a calculator. Okay, the rest of you hang on a sec. We're going to have the answer in a minute. I see 2 calculators going. Any luck on that? Hush up for a sec. It's too big. You can't compute it on your calculator. Can you? No, it's too big. Okay? I used a program called Mathematica to do it. It's this big. It's way out of sight of any of the numbers we've even been talking about for the Rubik's Cube. It is absolutely huge. Okay? So what I'd like to tell you a bit about next is how we can rearrange people. We've counted how many combinations there are, and the joy in the Rubik's Cube is how you change the arrangement of things, right? So let's consider that we have people just in a line, and what I'm allowed to do is pick up two people and switch positions and put them back down. And let's say my goal is to sort these people, alphabetical order by their names, but here I'm just calling them 1, 2, 3, and so on. So if I have 7 people, I know that the total number of possibilities is 7 factorial, and that your calculator would do. That's a bit over 5,000. And if I wanted to sort people, and my only operation is I'm allowed to take 2 people, switch the order, and put them back down, then in the worst case, how many moves is it going to take me here? Well, I might have person 1 off in the wrong place. So I take whoever is where person 1 should be, and I switch 1 with that guy, right? I do the same with 2, the same with 3. So it's going to take me 6 swaps. And more generally, if I had n people, it's going to take me like n swaps. Well, n minus 1, to be honest. But you know what? Computer scientists always forget about the plus or minus 1. It'll be a relief to some of you who always get marks off on your math assignments because of your plus or minus 2 or 3. By the time you get to analyzing algorithms, you don't care about those plus or minus 1s. Now, what if we had a more restricted thing where we're only allowed to swap 2 people who are already standing side by side? So how many moves then is it going to take to sort my list? Well, the first person might be at the wrong end of the list, so it's got to swap with the next neighbor, swap with the next neighbor, until it gets all the way down to the first position, right? So 6 moves just for person 1. And in the worst case, 5 moves for person 2, and so on. And we're going to get this number here. So you can do the arithmetic. But more generally, if I had n people, it's going to take something like n squared swaps. In fact, n squared over 2, but again, computer scientists even get lazy about the multiplicative constants. So let's consider one other scenario. What if we can only swap with neighbors that are 2 away? So for some reason you can't swap with your next neighbor, but just the one away. How many swaps is it going to take to sort the list this way? You might think it's like half because you get to jump down the list faster. But in fact, this is a bit of a trick question. Someone sees an answer. The first part of the answer, which I heard clearly, was that it's unsolvable, which is the right answer. If you think of the people in the odd and the even positions, they don't get mixed up, right? So we cannot always sort. That's a little bit what's happening with the Rubik's Cube, right? There's the corner cubies and the edge cubies, and they don't mix up. They stay separate. So here, the total number of possibilities we can get if we can only do these kind of swaps is not the whole 8 factorial possibilities, but just the 4 factorial mixing up of the light blue times the 4 factorial mixing up of the dark blue guys. Let's look at one other combination. What if I can only insert people 2 places away? So you have to imagine you're not sitting in your chairs, but you're standing up. So you can move aside a little when a person comes into the list. So suppose I can take a person and insert them 2 places away into the list. Now here, it is actually possible to get every person into every possible position in the list, but it is not possible to get every permutation of these 8 guys. And the reason is a very interesting one. Which is you have to think about what this operation is doing to a certain value, namely the number of pairs that are out of order. If we look at this example up here, it's only 5 that is out of order, and it's out of order with 1, 2, 3, and 4. So that's an even number. 5 is out of order with 4 things. Everyone else is right. If you look at 6 and 7, they're in the right order. Now when I do this kind of insertion, 5 hops over 1 and 2 and sticks itself in between 2 and 3. That number, 4, goes down by 2. Whenever I do this operation, I'm only going down by 2, or changing by 2. So I cannot sort the permutation that has 2 and 1 in the wrong order. So the total number of permutations I'm looking at in this scenario is not the full 8 factorial, but half of that. Because half of the configurations are the wrong parity, and I cannot get to them. And we'll see that that also is coming up in the Rubik's Cube. Okay, I had this picture to show, well, what if you're good at parkour and you can jump with the neighbor in front of you when you're sitting in an array, but maybe I'll skip that one for now. But I would like to mention one other thing that comes up with the Rubik's Cube, which is, what if the people are colored? And I don't care, I want the ones who are wearing red to be on one side of the room and the ones wearing blue to the other side, but I don't really care about their identity beyond that. And that's certainly what happens with the Rubik's Cube, right? I don't care if different blue things are mixed up. I don't know the difference. So here we have fewer possibilities. For example, here, instead of 8 factorial combinations, I should divide by the number of combinations where I just change the red guys amongst themselves. Okay, one more thing I'd like to tell you about permutations. Thank you, that's better. Permutations do not commute. Now, some of you may have heard about things commuting. Plus and times do commute, though it's pretty boring to learn that about plus and times because it's like breathing, you know that. So 3 plus 5 is the same as 5 plus 3. Also 3 times 5 is the same as 5 times 3. The abstract way to write that is if I have AB, it's the same as doing BA. And another way to write that is if I do A and then B and then A inverse and then B inverse, I'm going to get back to where I started, the identity. Like 3 plus 5 minus 3 minus 5 gets me back to 0. Now, these swaps, these permutation operations do not commute. It matters what order I do them in. So if I look, for example, at this swapping neighbors, and I say A is swapping the first 2 guys and B is swapping the second 2 guys, then if I do this in the order AB, I'm going to get the permutation that starts 2, 3, 1. But if I did it in the other order, I do B and then A, I get something else. And we saw this also in the Rubik's Cube. If you remember that video we watched with the right inverse, right down, that is exactly of this form of AB, A inverse, B inverse, and it does something very useful. It does not put the cube back to where it was. It rearranges things. So the moves in the Rubik's Cube do not commute. Now, I was going to tell you about permutations applying to the 15 puzzle, which some of you may have seen in this version of it. How many have seen a puzzle like this? Sometimes you see it with numbers, 1 through 15. And this is another case of permutations. And it's not as much fun as the Rubik's Cube. It was a craze 100 years before the Rubik's Cube. There are actually more possibilities here, and God's number, like the minimum number of moves, is actually higher for this, but it does not make it a more fun puzzle for some reason. So if you are thinking, how could I design the next Rubik's Cube, that craze that sweeps the world, you have to think of something that involves permutations, but more moves is not necessarily the better thing that you want. It's more fun for people when there's not 2-dimensional geometry, but 3-dimensional geometry. Anyway, but I think I will skip the details on this because I'd like to instead tell you a little more about the Rubik's Cube. So in what way is the Rubik's Cube a permutation group? Well, really, if you think of undressing the cube, there it is naked, and we've taken off all of the stickers. We have these 54 stickers, and they go back on some arrangement on the cube, right? So a rough count would be that we have these 54 stickers, we have 54 factorial ways of putting them on, except some of them are the same color, so it doesn't matter if we mix those up. So that's why I'm dividing by 6 factorial, 6 times for each of the faces. Now, the thing is, we can't get all of these permutations because we're restricted by what the moves are on the Rubik's Cube. So I'd like to show you at least some idea of why we get this 43 quintillion number. How does it come up? And we now have a little bit of machinery to show that to you. So it's 8 factorial, which is counting how many corner cubies were there. There were 8 of them. And in fact, you can switch them into any order. You can say this one, I want it to go there, and that one should go there, and so on. It's possible to do that in the Rubik's Cube. So we get 8 factorial there. And now, once a corner cube is in a certain position, there's still the question of what the colors are like. And there's 3 ways that the colors can be. And 7 of those corner cubes can have their colors interchanged. So that gives us a 3 to the power 7. Excuse me. And then we need to look at the edge cubies. There's 12 of them. And can I get them in arbitrary positions? Well, not quite. There's a parity thing that goes on in connection with the corner cubes. So in fact, we don't get all 12 factorial, but we get 12 factorial over 2. And then the very final term is 2 to the 11th, and it's because those edge cubies have 2 colors, and I can switch the order of the colors. And I can do that for 11 of them, and the 12th one is fixed. So this is the expression that when you multiply out is what gives you that 43 quintillion. Now, for bigger cubes, one could use similar arguments. I won't go through the actual counting, but I would like to at least go through this exercise of saying how many of the corner cubies are there, how many edge cubies, and how many of these, well, the center cubies now proliferate in these bigger cubes. So first of all, corner cubies, there's still 8, right? Even if the cube got bigger, there's still only 8 corners. How about the edge cubies? So I want to express this in terms of n. I have a picture here that's of, I don't know, what is it, 7 by 7 or something. But I want to express in terms of n. How many of these little edge cubies are there? N minus 2. Along a single edge, that's right. There's n minus 2 along the single edge, and then you have to count how many edges are there on the cube. So we're going to get 12 times n minus 2. That's very good. Now, finally, we want to count these little cubies that are like in the middle. They have only one colored side showing. Can someone see what the formula for that should be in terms of n? 6 times something, I'm hearing that. That's very good. And what is the something? Yeah, we need to square something. It's n minus 2 squared to get how many are on one side, and then I need to multiply by 6 to get all the sides. So in terms of solving this, the corner cubies are the same as even for the 3 by 3. The edge cubies, well, there's more of them, but it's growing linearly. It's n. And it's those center cubies that are going to cause us the trouble. So coming back to this result we showed, do people want to pay attention still? Thank you. This result we put in a paper this summer showing that the rate of growth of God's number for the bigger Rubik's cubes behaves like n squared over log n. There's 2 parts to that, and I'd like to show you at least the first idea of each part. One part is to show that this God's number is at least this big, and the other is to show that it's at most this big. So showing that it is at least a certain size is actually a fairly easy thing, and I'll show you the idea for the specific case of the 3 by 3 by 3. So the question to think about is how many configurations can I reach just by doing a single move? So we have to figure out how many different moves are there of the Rubik's Cube, right? So I have a certain number of faces, and for each face I have 3 possible choices I can do, right? I can turn it 90 degrees, turn it the full 120, or I could go backwards, counterclockwise, or equivalently 270 forward. So it's, can someone say how many that is? Six times 3, it's this number 18 that for some reason Jeff was talking about in the introduction. So there's 18 possible configurations that I can reach after a single move of the Rubik's Cube. So to put it the other way around, how many configurations can I solve with just one move? Just those 18, right? So you might say, well, are we there yet? I've only got 18 configurations. No, there are 43 times 10 to the 18th configurations. So I certainly have to consider 2 moves or more than that. And after 2 moves, I can get to 18 configurations with the first step, and then times another 18 choices for the second step. So I get to 324, and I'm still very far away. And I have to go all the way up to 16 moves to even get in the right ballpark of how many configurations I can reach. Now, in fact, we know that God's number is at least 20, and here my argument is only showing 16. And to get the rest of the way, you need a more like computer search to get there. But this idea is at the heart of our lower bound for the general n. Now, let me tell you one idea about the upper bound. So why is God's number growing as slowly as this? Why is it such a nice slow growing function? And the first idea is to say, well, we need a method here to solve a giant Rubik's Cube using not too many moves. So our idea is you first do the corner cubies and you do the edge cubies. And the thing we really have to worry about is those masses and masses, this 6 times n minus 2 squared of the center cubies. So the thing we observed is that in the same way that these corner cubies can only go to other corner positions, there's some structure like that that happens for these multiple little cubies in the middle. It's not true that I can swap one little cubie here with its neighbor. That can't happen when I turn a Rubik's Cube. If I think about one little dot, like this one with the pink star, and I say, how many different places can that go to as I turn the Rubik's Cube? That's what I want to know about as a first step here. So think about it. If I look at that little pink star and I do a right turn, it's going to go to a new place on the right face, right? And if I do another right turn, it's going to go to a third place and even to a fourth place. But that's it from the right turns. Now I might also imagine taking that slice of the Rubik's Cube and turning it on that axis, which would put my little star there. And then there's another 4 places on that face it can go to. All right? And another 4 places here. So how many places can that little star go to? Yeah. 24. That little star can go to 24 different places. So even as n gets very big, one of these little guys can only swap around into 24 places. And that's the secret to solving bigger Rubik's Cubes, is you only have to see how to solve the group involving these pink stars. And so I have 24 cubies in one of these clusters. And how many of these clusters do I have? Well, that comes back to how many of those little cubies, but now I divide by 24. So there's a lot of them. But the idea is to solve each one with some finite number of moves. And the really basic move at the heart of that, so this might be interesting to those of you who know how to solve Rubik's Cubes, is there is a way for me to swap the places of those 3 stars while leaving everything else fixed in the Rubik's Cube. There's some finite sequence, you know, like this right inverse, right down. It's going to be a longer sequence, and the effect of it is to switch around those 3 positions and not touch anything else. Okay, and that is the secret to solving these bigger Rubik's Cubes, because I have my 24 things, I want to get the right permutation, I know how to do 3-way swaps. So I just do those until I've solved those 24, and then I go and look at the next 24, the next QB cluster. So the final thing, this gives us the n squared, that rate of growth of n squared, and we actually wanted to get below that, so that was the one new ingredient. And to do that, we had a way to parallelize. So instead of solving one cluster, then solving the next cluster, then solving the next cluster, we took 2 of those sequences of moves and sort of put them together so that we get to reuse some things. And so I'm trying to show this with a picture here where the cluster with the pink stars, I might have some way of solving that. It might involve doing the move T, doing some other things, and then putting T back, because we do want to get the other things back to their ordinary place. And for the blue cluster, I might have turns that involve doing T, doing some other things, and then doing T back. Instead of doing those one after another, I'm going to do them this way, where I do t once, do the pink moves I like, do the blue moves I like, and then do t back. And that's how we save that extra last little bit. Okay, now you might say, that was all very theoretical, this n squared over log n, but I really want to know what is God's number for this cube. And our proof doesn't say so much about that because we were doing this trick of ignoring the plus and minus ones, ignoring the constant factors. So if you want to know exactly what is God's number for a bigger cube, you have to study these constants. And the best thing we know is that it's somewhere between 12.9 and this 16 million up there. So that's kind of a big gap in terms of the constant. From examining what happens for 2 and 3, we know that the answer ought to be about 3.5, but we couldn't show that. On the other hand, we could plug into our proof and see that for the 17 cube, God's number has to be at least 347. It's probably much, much more than that, but that's the bound that we could show. So is anyone going to do speed cubing on the 17 by 17? I don't think so. That's an awful lot of moves to have to do. And there still are open questions for computer scientists in here. And one is that even though we found this bound on how many moves it takes, we were not able to show whether there's a nice algorithm, so one with a running time that isn't astronomical, to find those solutions. I hope I've given you a little bit of a flavor of some of the math and some of the computer science behind the Rubik's Cube. If you're interested in engineering, it's the mechanical design of this that's fascinating. If you're interested in math, it's like the numbers of configurations that's fascinating. And if you're a computer scientist, it's having algorithms to do things like this, solve permutation groups and solve Rubik's Cubes. That's interesting. And although Wikipedia is occasionally a bad source, there's, random people posting in Wikipedia. In the case of the Rubik's Cube, the Wikipedia page is actually really good. So if you want to learn more about things like this, the Wikipedia page is the place to look. Okay, thank you all very much.
Thanks, Anna.
Do we have time for questions?
Yeah.
Okay.
We have time for a few questions.
Shh.
Thank you. We have time for a few questions. While you're thinking, I'll tell you my experience. When I was in grade 5, there was a Rubik's Cube craze that went through my grade school. And I'm a little embarrassed to say that I solved it by taking the stickers off.
Yeah, this YouTube site that I was pointing out tells you first the other cheat, which is to take apart the Rubik's Cube. So you don't need to take the stickers off, because that's actually, you're not going to get them on as nicely. But you can twist and get one of the little cubies out and get it back that way. That's the other way to cheat.
Are there any questions for Anna? I'll bring the mic over, okay?
Okay, if you could hush, then we'll hear this question.
Hi. Hello? Yes? Okay. My name is Alex, and I do have a question. Okay, I'm not sure how familiar. I'm not sure how familiar you are with physics, particularly astrophysics. But when they get to such large. Thank you. When you get.
Is it me?
Testing. Okay, but when you get to such large numbers that they could be considered infinity, right? Is it possible to get a Rubik's Cube that's large enough where its God's number could be considered that large?
So that's a nice question. The question is, when you get so large, could you consider that to be infinity? In some sense, no. So even a hugely, hugely large number is still a finite number. And mathematicians make a distinction between something that's very, very large and infinity. So the natural numbers, the counting numbers, that's an infinite set. There's always a bigger one. But no matter how large a specific number is, it's still a specific number. It's not infinity. So,
Do you have any other questions? Somebody wants to test the feedback in the system?
I actually have a question for you guys. How fast can some of you solve a Rubik's Cube? Sorry, one at a time so that we can hear it. Sorry? 8 seconds. 38 seconds. We have 38 seconds. Does anyone do it faster? 45 seconds. A record of 25. Okay, I think you guys should have a competition at lunchtime.